Okay, so hello everyone. So thank you again to attend our this week Progress in Efficient AI Seminar talk. And today we're glad that we have the Professor Atlas Wang from the UT Austin to give this talk, the lottery ticket hypothesis for large-scale pre-trained models. And Professor Wang is currently assistant professor in the EC department at the UT Austin. And he also holds a visiting research position at Amazon. He was once in the Texas A&M University from 2017 to 2020, and he received his PhD in EC from UIUC and advised by Professor Thomas Huang. Professor Wang has a broad research interest in the machine learning, computer vision, optimization, and their interdisciplinary applications. And most recently, he studies automated machine learning to optimize robust learning, efficient learning, and graph neural networks. He has received many prestigious research awards and scholarships, including most recently an Arm Research Office Young Investigator Award, IBM Faculty Award, JP Morgan Faculty Research Award, Amazon Research Award, and Adobe Data Scientist Research Award, and the Young Faculty Fellow of Texas A&M, and the 4 research competition prizes from the CVPR, ICCV, and the ECCV. So now let's welcome Professor Wang to give this talk.
Thank you, Professor Yuan, for making this very nice introduction, and thanks everyone for sparing the time to attend my talk. Today I'll talk about lottery ticket hypothesis. Actually, I was a bit surprised when Bo told me I would be the second person talking about this sim in this wonderful seminar series, because Jonathan came here to give his talk 2 weeks ago, and I'm sure this must be wonderful. So I have to specifically check with Bo and Jonathan that my talk didn't overlap much with Jonathan's talk, so I can have the comfort to give this talk. So today I will talk about a particular application, or say observation, of lottery ticket hypothesis in a specific context, that is large pre-trained models. So this work is led by my excellent PhD student, Tianlong Chen, and also thanks to our excellent collaborators, Jonathan and Michael from MIT, and Shiyu, Sijia, and Yang from IBM Watson AI Lab. So before we talk about, lottery ticket hypothesis, let's first zoom out and take a look at the big picture. I guess people more or less know about lottery tickets hypothesis is about sparsity and pruning, but what's its exact location in that big picture? I'm trying to categorize the pruning method into from a few perspective angles. The first question is what to prune. So from the basic one, brain damage, it's to remove the small magnitude element by element. And those element-wise pruning, we call that unstructured ones. The nowadays more popular options are structured prunings, which remove elements in structural groups, such as channels in convolutional network. And also your pruning can be done in a layer-wise local fashion or done in a more globalized strategical fashion. So those constitute the option to the first question to answer what to prune. And the second question is how to prune. Like I mentioned, the magnitude was the one most natural option to remove element whose small magnitude is believed to indicate less importance to the network. But it has been later recognized that this is not necessarily true. The element magnitude is not necessarily the contribution to the big prediction ability. So we have seen more options ranging from gradient-based to learned importance score to information theory, and the list can go longer. The third question is, when should we do the pruning? Well, traditionally, and even still now, 90% of works will tell you the pruning is a post-processing technique that you first train an over-parameterized model and then shrink its size by removing those unimportant elements, either structured or unstructured, and by whatever criterion you prefer. But recently, there has been a growing interest to see if we could push pruning earlier in the training process. So is this magic of over-parameterization necessary and have to persist until the last minutes of the training? And many research evidence told us, no, you don't have to do that. You could do pruning in the middle of the training, and there are some occasions arising our particular interest that you can even do pruning even before the training has ever started. So that literally leads to a design philosophy of sparse neural network from scratch. And lastly, you could do prune once, you could do prune multiple times, so lead to one-shot strategy and iterative strategy. So from this big picture must be incomplete, but perhaps it suffices for us to locate where we're going to be today. For lottery tickets hypothesis, it will be defined by the following 4 attributes. It will be unstructured pruning for most of the cases. So it will remove element by element. It so far mainly rely on magnitude-based pruning. I'm not saying those more fancier options are not useful here. Just by convention, unstructured magnitude pruning are still the default option. We usually will do iterative, iterative unstructured magnitude pruning. And lastly, but more importantly, lottery tickets armed to do pruning before training. So we want to find a sparse neural network and train that from scratch. So now let's zoom in and dive into this special setting of pruning. I was trying to find a definition for lottery ticket hypothesis precisely, and turned out that I find myself cannot do a better job than Jonathan. So I directly do a screenshot of Jonathan's award-winning paper for his definition of lottery ticket hypothesis. According to Jonathan, lottery ticket hypothesis refers to a randomly initialized dense neural network must contain at least one subnetwork that can be initialized such that it will be trained, in isolation to match the test accuracy of the original dense network training with the same training recipe. So this work, I guess everybody knows, won the iClear 2019 best paper. And as soon as it won the best paper award, it immediately attracted many people's attention, including myself, who traditionally work on sparse optimization. It's because this is something, well, I would say hit me as a big surprise back to the time when I first read this paper. Well, because in deep neural network, it's well known that it relies on gradient optimization, and the deep neural network is not a particularly good friend for gradient propagation. When it goes deeper, or when the network it goes thinner, the network's gradient propagation will be problematic, even that's a dense network. So if we start from the very beginning, we even further shrink this dense network to be a narrow, thinner sparse network, then wouldn't that be the case that information propagation bottleneck will more easily occur and the gradient will be very unhealthy? Indeed, that has been the common belief of people, the people before lottery tickets was proposed. People basically thought that's also part of the reason why people basically thought pruning to be a way that can only be done after over-parameterized dense training, because you have done the difficult part, you have found the solution, so you only need to fine-tune the solution a little bit afterwards. Then only in that case, the sparse neural network are believed to be trainable. But lottery tickets are telling us, no, you can do much better than that. You can do a longer shot from the random initialization to the last end. And with doing that, this special sparse network called winning ticket would give you better or at least a comparable result using the same or shorter training time. The model has notably fewer parameters and is trainable from the beginning, especially because the model is compact from the time zero. So the whole training process will see significant savings of the flows of the training or other training costs as well, because the model is smaller, less free parameters, and it does not come at the price of longer training time. It also does not compromise the accuracy. So this is a very attractive free lunch, right? But this free lunch by that time only looked attractive at the first glance. It's no longer that attractive if you look at how this Spark network was actually obtained. So the key question here is, yeah, you can enjoy this free lunch as long as you know which subnetwork is winning, which sparse network is chosen. So how to choose that? Jonathan's solution was a surprisingly simple approach called iterative magnitude pruning. Specifically, start from a randomly initialized dense network. We will start training it to let's say two convergence and do an ordinary pruning. So this pruning, for example, if we want to achieve a sparse neural network of 90% sparsity eventually, we may do a much wilder pruning in each round. For example, in first round, we may just remove 10% to 20% of the element. So we get a relatively sparse network. Now we have obtained this connectivity. We will totally discard the weight we have trained at this round and unroll this trained sparse network back to the random initialization to just keep this sparse connectivity. But the weight, the remaining weight is rolled back to the random initialization. And we repeat this process, do that again, and remove a few more connectivity, and doing that repeatedly until we reach the target sparsity level. So that takes multiple rounds of magnitude-based pruning. Then eventually, with this sparse connectivity map, which is usually highly sparse, up to 70 to 90% or even higher, along with the original initialization used for the dense network, they couple together are called the winning ticket, and can be trained from scratch to meet all the assumptions on the last page. So it may look, I'm not sure if you share the feeling, but when I first look at this algorithm, I totally didn't get the point. I mean, well, you told me you could get a much compact network that can be trained from scratch, and you told me all the benefit of training resource saving and blah, 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 blah. But okay, in order to get that very sparse network, that compact network, I have to do the training multiple rounds, and literally cost me multiple times more training resources rather than just training the dense network from the very beginning. So if that is true, why would I bother looking at the lottery ticket? That was a very valid question. And that confused me for a while, because so let's say that the first lottery ticket paper proved the concept of the existence, it's an existence proof of trainable sparse network, but it didn't immediately provide a link how this could be practically useful. Its practical usefulness left to be verified by many subsequent works. And in the next page, I have summarized you a few follow-up works along this path, and I will point out to you some interesting points which will eventually lead to our work. The first interesting work, similarly done by Jonathan, shows that, well, if you the lottery ticket hypothesis, while verified to be useful on relatively small data set like MNIST or CIFAR, does not immediately scale up to larger data set such as ImageNet. And Jonathan and his collaborators found that that's because the initialization stage might be noisy. And for sparse neural network, the most difficult part is perhaps not to run the long optimization trajectory for most of the time of the training. The difficult part is instead the chaotic, difficult optimization stage due to random initialization. It's at the very beginning. So they propose an empirical trick called rewinding, which means instead of to ask for a sparse network that trend from the random initialization, let me relax a little bit and use the early stage trend weight of the network instead of random initialization, and ask my sparse network to trend from there. You can consider this as to give this network a little bit of push, to have it to a warm start. And that is found to be substantially useful to make lottery ticket work on ImageNet scale and large scale models. So that also gives us a hint that lottery tickets seem to be benefiting from a warm start initialization and from some locality-based training, because give it a warm start literally supplies the starting point a bit closer to the end point, right? So it helps the locality of the training. So let's put the two keywords, the warm start initialization and the locality in your mind, and because those are very relevant keywords afterwards. The second paper, Destructing Lottery Tickets, was done by OpenAI in Europe 2 years ago. And it basically discovers that lottery tickets can work even without training the weight. So given a very overparameterized deep network, it's even possible to find a sparse mask that can work with a random initialization weight without adding further training and deliver substantial non-trivial classification accuracy on several benchmarks. So that just conveys a strong information. That is, neural networks are universal approximation, perhaps so we all know that neural networks are universal approximators. This paper basically tells us another possibility, of advanced possibility, that neural network can be even as universal approximators or close, even if no training happens, as long as we can find a suitable mask, and the mask itself could be viewed as a training way that encode useful information specific to the dataset. They have summarized a quote called masking is also training. Another important, so this paper basically passed the important message that we should pay more attention to the sparse architecture as they can be as informative as the trend weight itself. And another important message conveyed by this paper is they find another possibility to warm start the lottery tickets scale up experiment. That is to keep the science of the initialization. They find that for even you to give up the random initialization's weight, magnitude, but just keep the signs of this weight, just positive or negative. Recording them are often sufficing to keep the lottery ticket work on some scale experiment. So that tells us, to me, that provides another side evidence. Lottery ticket hypothesis benefit from locality. Because if you think what it does mean to keep the signs, it means that instead of recording the exact initialization point, I'm recording the hyperbolic subspace where the lottery ticket initialization was residing in, and experiments show to find that locality neighborhood for the initialization is enough for lottery ticket to work in some case. So that's another supporting evidence for locality. The third paper done by Facebook AI by Aaron Marcos and his colleagues was the first empirical study to show lottery tickets has transferability. One quote that was to be memorized from their paper is, they could identify a marching ticket, found a winning lottery ticket, found on one image classification dataset, and can work for other image classification dataset too, for the same model, of course. So that shows the lottery tickets has a possibility of transferability. And let me also remind you, transferability will be another keyword of today's talk. I will talk about it why. It will talk why later in a later slide, because transferability offers a possible way out of the expensive cost of finding lottery tickets. It can resolve that contradiction. And for the next paper, lottery the linear model mode connectivity, I'm sure a lot Jonathan talk about it. That basically shows you can have more than one lottery ticket and they are connected. That's an interesting landscape study of lottery ticket solutions. The next paper comes from our group in collaboration with Rice University. This paper shows that lottery tickets could be found in the early stage of the training. Remember that in the last page, we said it will take iterative pruning to find a lottery ticket, and each iterative pruning will take nearly the same training cost of a 4-round training. Our paper shows that you don't have to do that. Early training suffice to find if you just want to find a mask, because anyway, you want to give up the weight, you just want to find a mask. And we observe that sparse connectivity mask actually get stabilized much earlier than the weights themselves get stabilized. So it's possible to use some graph-based measures to indicate a stabilized sparse mask and stop training by that time point. And that have led to efficient training of deep neural networks by lottery tickets, because now lottery tickets can be found by a much reduced training schedule.
I have a question.
Please.
You mentioned the third paper. You say that in the paper, you mentioned that the matching ticket can be transferred from one data set to another. So do they have any theoretical justification, or is this just some heuristic observation?
It's a heuristic. The theoretical work in lottery tickets hypothesize are hand countable. We can talk about that if you're interested, maybe after the talk. The theory are still under open development.
I see. Thank you.
Thank you. Okay, so for the lottery tickets, to our best, so for the early bird ticket paper from us in the iClear 2020, to our best knowledge is perhaps the earliest work bring lottery tickets to actual efficiency of deep learning in training. So that was that was one. And another work I have to mention is a concurrent work by Jonathan, published later in ICML 2020. So they have a very interesting observation. They basically tried a different kind of tricks and showed how to scale up lottery tickets and find no such trick can perform more effectively than the earliest trick called rewinding. If you still remember, that means a warm start initialization with an early stage wait. But there is one exception. If you use a self-supervised pre-training to initialize the network, and then use that in place of the random initialization, then you no longer need to do rewinding. Because self-supervised initialization could be viewed as a warm start by itself, and it provides that desirable locality for the training. So the training does not need to go very far away from the initialization, as we usually assume in the transfer learning case, right? So this provides a very important hint for our work. There are apparently many more works following lottery tickets in various ways, but I'm just picking a few that will provide useful concept connected to our talk today. The main take-home message and also the consensus of those papers listed on this page are: random initializations seem to be not that stable to make lottery ticket hypothesis work. And some early training seem to be indispensable in current regimes to make it work. That early training could be in the form of rewinding, which is reuse itself's early training trajectory. Or it could be self-supervised initialization, that is to transfer some warm start from other surrogate training tasks. Either could work. And also lottery tickets could benefit from transferability. So the warm-up initialization and the transferability are two consensus we learned from the prior context and critically motivated our work. Now, after the background, I'm finally moving to our work. Our problem is simple and clear. We want to study lottery ticket hypothesis for large pre-trained network models. So this is a research question, and I guess I don't need to emphasize more the significance of pre-trained models nowadays. We see a lot of media splash from that, right? From the BERT model to the Sinclair model, to the recent GPT-3 model that everybody is playing with. Those models are powerful, but those models are not tiny at all, right? So while they are good, they are also expensive, and the reason the models are completely beyond the typical academic capacity to play with. Not to say, well, now we are sitting in a seminar called Efficient AI that usually talk about the techniques that can be deployed on mobile or other resource-constrained platforms. I'm afraid for many models like Sinclair, and OpenAI, perhaps it does not fall under your typical consideration how they can be deployed in the mobile devices, right? They are too big, they're not efficient. So we set up this goal because we see the practical relevance. We could have made them efficient, and the lottery tickets might be the right tool. So why this goal? On the methodology side, it's a new interesting question. And I already said, for practice, pre-training and transfer learning is becoming the central regime. Computer vision, natural language processing, and recently even for graph neural network and bioinformatics. So if we could compress those big pre-trained models, for example, to specify them using lottery tickets, this would be a blessing for people either who just want to deploy them for inference, and maybe even for people who want to transfer them, because the pre-training models value is manifested by downstream transfer learning, right? So if we could have such a sweet point that we could have a sparse network, once we tune it, it transfers as well as the original dense pre-trained model to all downstream tasks, then that's such a sweet point, right? That means that this sparse network could be totally replacing the original dense, gigantic pre-trained models. Note that when we talk about this transferability, it is already significantly a higher standard compared to the previous definition of lottery tickets. Because the previous lottery tickets is defined on the same data set. And even there exists a previous transferability study. It means transferability from one task to the other within the same model. For example, transfer a ResNet lottery tickets from ImageNet to CIFA. And now we are talking about transfer a pre-trained model like BERT universally to all the downstream tasks, like the 11 tasks on the GLUE benchmark. So that is a heterogeneous task transferability from a pre-trained model that, to our best knowledge, wasn't touched by previous study. This is not only useful, but also very appealing to make lottery tickets practically relevant. Why? Because now previously we are complaining about lottery tickets because to find a mask, it will need to train the network multiple rounds essentially, and the mask can still only be applied to train the same model on the same data set or similar data set with similar tasks. The cost doesn't sound economic. But for pre-training, the keyword is reusing, right? A pre-trained model could be transferred for numerous downstream tasks. So if we could really get a universal mask that is the same effective to the different downstream tasks, and then the cost of finding that one sparse mask, one lottery ticket, however expensive that is no longer expensive because it can be reused by transfer learning. That reusability gives the new blessing why lottery tickets is practically relevant. So that's the practical motivation. And rolling back to the methodology motivation, we also feel we are naturally motivated because look at those keywords. Pre-trained weight naturally provide a sense of warm start initialization and provide the locality push for the training regime. So with the pre-trained weight, we are perhaps also able to get rid of the somehow ad hoc rewinning scheme and find a lottery tickets mask directly on the pre-trained weight without whist and bells. This is also methodologically simplifying lottery tickets execution. So from both sides, you can see we are naturally motivated why we want to study this problem. And the methodology side is notably motivated by previous work, study the locality and warm start initialization for the lottery tickets, how it helps the lottery tickets scale up. And the practical side is motivated by the previous transferability study of lottery tickets, but significantly augmenting its scope. I just want to make sure our context is very clear with regard to previous work. So from this page, I will bring you a few empirical studies, which may sound boring if you are theoretically Savoy, because perhaps in the next 10 pages, I will talk about nothing but empirical experiments. We have conducted a few empirical studies on lottery tickets, and our first subject of study is BERT because of its practical relevance apparently. I have summarized a few findings here for you. So you're welcome to check our paper, but I would rather to directly jump to the conclusion without going through the experimental settings in the paper, because number one, I feel they're easy to understand. Number two, we really did a lot of experiments that will take me quite a while to elaborate on different experimental settings. So please allow me to a little bit lazy and bring you directly jump to the conclusions. Conclusion one, using the standard lottery tickets, iterative magnitude pruning, we are able to find winning tickets in a range of sparsity levels between 40% to as high as 90% sparsity in the BERT models that can really work on standard glue and squad downstream tasks. Work means universally transfer. That is the sparse model, once fine-tuned to fit different downstream tasks, they can be fine-tuned using the same sparse mask and the same initialization weight, and just fine-tuning and being fine-tuned as normal. So that really tells us the sparse mask basically can replace the role of original dense model, which is a big blessing if you think it over. And another thing I want to emphasize is those sparse networks are found at pre-trained initialization rather than adding amount of training. So there is no rewinding involved no empirical weight. We just use the official pre-trained weight of BERT. And also, as in previous work, we have verified the sparse masks are non-trivial, which means if you use random pruning, random initialization, dropping those pre-trained initialization weight, or any other non-lottery ticket style pruning, the performance cannot match the performance delivered by our sparse mask. And we have also yielded optimal lottery tickets at roughly 70% of sparsity. 70% means 70% of element being removed and set to 0. You found using the standard BERT pre-training task, which is masked language modeling, universally transferable with the best performance and matching accuracy on many of them, or even better. So as I mentioned, in this study, the biggest caveat of previous lottery ticket work, that is, in large-scale settings, matching subnetwork or winning ticket can only be found early in training, has disappeared. And there are indeed universal subnetworks that could replace the full BERT model without inhibiting transfer. So this is so for NLP, while pre-training is non-central, those results demonstrate our lottery ticket observations hold for the example of the class of learning algorithms with pre-training. And it also reveals the tantalizing possibility that we could train smaller network from scratch, even for the transfer purpose. So here I am going through a few key research questions and experimental designs we had in our paper. So this was published in Europe last year. So we have discovered an experiment to compare the winning tickets quality with different pruning solutions. And we can show that the lottery tickets can achieve a much higher sparsity than other random pruning or other pruning strategies without compromising the performance. We have tested rewinding and shows it does not improve additional performance on top of the pre-trained weight. And standard post training and we also compared this universally sparse mask with standard task specific training. That is, we could first do the pruning and fit the downstream task. And for each downstream task, we will do a post-training pruning to find a mask using the standard iterative routine. That is apparently a stronger and more costly baseline than lottery tickets, which rely on one mask to transfer them all. And our experiment observed that our carefully found mask at the pre-training stage can match the performance of task-specific pruning as well. We have studied the transferability of winning tickets and also observed the patterns in subnetwork transferability. An interesting observation I'd like to synchronize with you is we have did further studies to see whether the pre-training task here has any effect on the transferability of the found tickets. Because while BERT has the deferred training task of mask language modeling, but there are more language tasks, for example, those defined on the glue and the squad benchmark, they can all potentially become pre-training tasks. And we spend quite a bit of GPU resource in playing with them, switching between different pre-training tasks and test their mask transferability. And the result was a little bit surprising and interesting. We didn't find any statistically significant evidence that the pre-training task matters. But what we found instead is the amount of pre-training data matters a lot for lottery ticket transferability. It looks like mask language modeling discovers tasks that have the best transferability. For example, this one, you can see this mask MLM, mask language modeling found ticket can transfer to almost all the tasks with performance gains over baselines. And that looks like that's simply because mask language modeling has the largest training set among the 11 standard benchmark tasks. And if we reduce the training set size for MLM, its transferability will significantly reduce as well. So instead of task matters, our findings seem to suggest data size matters, and the sparse mask quality is affected by data volume. And you can find more experiment in our supplementary. I'm not going to more details here, but if you're interested in any of the experiment settings, you're welcome to ask now or after the talk. So that's the first course of study on BERT. And with some quite encouraging findings from the BERT case, we have proceeded ourselves to the next subject, which is where I come from, the computer vision field. Well, we are interested in turning from BERT to computer vision. Yes, because computer vision recently also see a resurgence of self-supervised pre-training, especially from last year. But we really see this as an interesting and independent research problem from the BERT case. Well, let's say I'm doing this not because we want another paper. We already have, you may be curious, you already observed on BERT. So what's the interesting additional bonus you could gain by observing another set of experiments in computer vision setting? Well, I may argue that this is indeed very interesting because computer vision self-supervision is more difficult, if I may say so, and more subtle than BERT. Here is why. First thing, pre-training BERT typically only use one self-supervised objective accepted all. We already mentioned called mask language modeling. But the pre-training computer vision has a huge wealth of popular options, ranging from a supervised fashion, like before this, well, the transfer learning it's not a new thing from last year, right? Even before self-supervision gains big fame, the transfer learning already being popular, and what we transfer is the supervised model pre-trained on ImageNet benchmark, right? So supervised training has certain transferability on computer vision tasks. And recently we have gradually switched to self-supervision, ranging from pre-text tasks such as impending, colorization, or reordering, to the more recently popular contrast learning framework. We have numerous self-supervision projectives, and it's quite doubting to check if there exists any universal conclusion that can be held by them all. Actually, we are super unsure before we do experiment whether this can succeed. The next point I have to emphasize is different computer vision downstream tasks are known to rely on different priors and invariances. For example, many of you perhaps know image classification calls for shift translation invariance, shift invariance. But for another task, for example, object detection, do we still need the shift invariance? We need a vice versa, right? Because object detection asks you to localize the important object. And if that object moves in the image, your bounding box should move, your feature should move as well. So instead of the shift invariance, we want to shift the covariance here for object detection. This is just one example I can use to illustrate how complicated the feature priors will vary in computer vision per different task. And third, of course, the BERT model have very different building block from the convolutional network typically used in computer vision. So the architecture differences may create another gap as well. So all those questions actually made us very excited to look at the computer vision, even we already have BERT. And we consider that to be highly risky research. So, but somehow, very fortunately, we have found our solution and observations can extend to computer vision to a certain extent as well. In computer vision, we are asking the same question: can we aggressively trim down the complexity of pre-trained models without damaging their universal transferability? And we look at a wider selection of models. For example, we have chosen 3 most popular and successful pre-training ways: ImageNet supervised pre-training, Sinclair pre-training, and Mocha pre-training, all on ImageNet. And we repeat our experiment on BERT to each of them. And we test them on 3 different computer vision tasks requiring very different feature priors, including image classification, object detection, and semantic segmentation. The conclusion is, in general, with a few failure cases, for most of the cases we look at, we get very similar observations with BERT. There exists highly sparse subnetwork from any of the 3 training options that can be universally transferable to the 3 chosen downstream tasks. Note that I'm not claiming not claiming this conclusion would generalize to all the possibilities because we only tried 3 pre-training and 3 downstream tasks. But note how general and how representative those tasks are chosen. I personally have some confidence it can extend to more pre-training and downstream strategies. So more specifically, for ImageNet supervised Sinclair and Moco, we can all find sparse subnetwork between 60% to 70% that can universally transferable to the 3 tasks. So that's a great deal of sparsity as well. And the same as a BERT case. You just need 1 sparse mask. You don't need to touch the pre-trained weight. So here, mask is all you need for all your downstream tasks. So without, I promise I don't want to go a lot of experiment details, but just a few, but I still picked 2 interesting experiments to share with you. The first thing is, in this computer vision task, we have tried to perturb the sparse masks found at pre-trained initialization because we got asked, and we asked ourselves, is this sparsity seems to come too easy? Come on, how could you be so lucky? Is it just because we are now obsessed with over-parameterization and every model in use is super parameterized, so sparsity can work easily simply because you have a wasteful of parameters? We're curious about that. So we conducted experiments to add different connectivity perturbations on the found sparse mask. And somehow happily, we observed that this sparse mask's perform transferability will very quickly degrade if we just perturb even as small as 10% of the found sparse mask locations. So it is sensitive to sparse structure change. And in other words, the mask is not just an arbitrary form of sparsity. It's a structural form of sparsity that is meaningful. Next experiment. We have also observed different pre-training sparsity structures found in their masks and their perturbation sensitivity. Our observation is the structure of ImageNet supervised pre-training and Sinclair pre-training are relatively similar to each other. And the Moco displays are somehow different sparsity. With all those results, I perhaps want to beg you to look at the finger on the right most closely. You can see, well, here the visualization is, we try to visualize unstructured sparsity through the lens of structured sparsity. What it means is, we have pruned the network to very high sparsity anyway. So as you can imagine, even we didn't enforce structural sparsity, there will be many filters whose all elements are removed. So we have counted those elements. So we have checked the filters and consider filters whose dominant portions of element being 0 to be a 0 filter. In this way, we observed a coarse-grained structured visualization of network sparsity for us to observe because unstructured sparsity is hard to visualize for large networks. You can see ImageNet and Sinclair basically have very similar observations on their naturally emerged sparsity patterns, right? Mostly concentrated on the lower layers. And Sinclair seem to be better than ImageNet with more structurally sparse filters in low level and a few more on the high levels. But what surprised us most is Moco. Moco, by just applying iterative magnitude pruning in lottery ticket style, could generate a great deal of natural structured sparsity, even without being specified to do so. Comparing with the two, those structured sparsity are naturally displayed more uniformly across the network layers. You can still see some great substantial sparsity in structural forms, even in the middle of high layers of networks. And overall, the ratio, I remember, in our definition, the structured sparse ratio of Moco is also 30 to 40% higher than Sinclair and ImageNet. One of our following up works is trying to explain why this happens, and we believe it's because of Morkel's momentum trailing behavior that create weight averaging and a smoother landscape. That's still ongoing work, but the observation is already here. And one additional observation is lottery tickets will work even better in terms of transferability when the pre-trained model get larger and larger and larger. So if you pre-train, the pre-training model scale up from ResNet 50 to ResNet 100 or ResNet 300, the transferability of the found ticket at extremely high sparsity will get better and better as well. This is in accordance with the current trend in self-supervised pre-training, right? Bigger pre-trained model transferred better, so are their lottery tickets. So I'm basically done with my with my experimental report. They're embarrassingly empirical, but I hope those observations will inspire some rethinking about how lottery tickets and pre-training could be naturally married together and provide some promise for tiny ML and efficient AI. Here I offered some discussions. I guess today here we sit a lot of expert in tiny ML. So I'm very superficial in that aspect. But from what I know, there is now a trend. It's now a trend in development to deploy speech recognition and some computer vision models on microcontrollers on other extremely low resource dev bots. So the field also start to bring complicated computer vision tasks to the microcomputer level. For example, my group last year participated in the low power computer vision challenge, and that is for video detection task, sophisticated enough. This year, they even started to look at video tracking. So those will call for stronger intelligence and the complicated models. And we view lottery ticket sparsity to be a very promising bridge to two different trends in the AI field. The larger and larger pre-training and the smaller and smaller deployment. Notice that lottery tickets not only give you a very compact deployed model due to its extremely high sparsity, but also lottery tickets, when applied on pre-trained models, can have strong transferability, so that can fit the need of personalization on downstream setting too, even the model has been deployed on resource-constrained platforms. That is a whole new scope, and that is not naturally bound with other compression means. Here, we did some simple mathematics. If you use a pre-trained dense 32-bit ResNet 18, the highest sparsity we discovered as lottery tickets in our CVPR paper is higher than 98%, sorry. And assume the backbone to be 80, so the parameter storage will take 60 to 700 gigabit. And gigabit after applying this high pruning ratio. And this is already close to the storage available to micro-embedding MCUs, right? And the shrinking it further is also straightforward since we haven't even considered using a small backbone. ResNet 18 is an unconventionally large backbone for edge applications already. So what if we use a shallow ResNet? What if we use MobileNet? Or what if we use some subsequent quantization? There are many possible venues to make lottery ticket models really possibly deployed on small edge devices. So here comes the regime I really want to sell to people who attend this talk. The new regime, the previous regime in pre-training is first pre-train a large model and deploy fine-tuning it for deployment. And if you want to compress it, the compression typically takes place after the fine-tuning stage. But I'm proposing to insert a new stage between the two. The lottery ticket mask found on the pre-training stage could be injected before any downstream fine-tuning and deployment ever happen. And by doing that, the fine-tuning process will also benefit from the compact and reusable sparse mask and save cost for the fine-tuning, the training process too. With that help, it's more possible to bring the extremely compact model to edge devices, even personalization or adaptation is needed. So we claim for this new regime, let's do pre-training and let's find this universally transform mask and then enjoy the benefit of deploying and fine-tuning. I would also like to append one more discussion on its practical hardware saving. Because if you are hardware people, you perhaps want to be able to tolerate me too much talking about unstructured sparsity, which perhaps nowadays common sense didn't translate too well into hardware resource saving. We are aware of that, and several points for your reference. First, it's nowadays that we already see some hardware support for extremely high structural sparsity, and for our sparsity level achieved 70% to 90%. Some existing accelerator packages, such as XNMPark, are already available for smartphone processors. We have tried to deploy one of our larger ticket models using this XNMPark on a smartphone running Quadragon. And for the sparsity, unstructured sparsity at 90%, it could achieve nearly 2 times speed up on real mobile phone latency. So there is help. And we also have parallel work currently in-house ongoing in my group to find lottery tickets at a structured sparsity. We do hope to make it happen soon. And lastly, I want to remind that the benefit of high sparsity could extend beyond just the training and inference efficiency. Sparsity to deep learning people are perhaps known for a long while as tools for efficiency, but the efficiency could go beyond just the training and inference resource. For example, the efficiency could also be data efficiency. Sparsity could constrain the hypothesized space and potentially save training data and become a strong regularizer for future learning. And recently, we have a parallel work showing lottery tickets can be applied for data efficient GAN training. This is another level of efficiency. What are the efficiency? Another possibility is if you wanted to communicate the sparse models instead of storage that, then those sparse models naturally save communication bandwidth too, in addition to saving storage and saving local training and inference costs. And what is that implying? It implying sparse training, sparse models and lottery tickets could become a good friend for federated learning, which love all those, saving storage, saving communication, and saving local training costs. And recently we have some work out on that aspect as well. With that, I'm ready to conclude my talk, and I have to give kudos to my student and collaborators, especially my student Tianlong Chen, who did the dirty work. I'm apparently doing nothing but shamelessly taking credit from my student hard work. So this work has attracted a few media attentions, including MIT News. We have a project page, and all our research code are open source and publicly reducible. So with that, I hope you would enjoy this big lottery in your research and hope you will draw your jack pocket out of that. And perhaps one last promotion, if you allow me. I particularly picked this date because I wanted to take this chance to promote an event that will happen in a few days. So this is a workshop, perhaps the first of its kind to study sparsity from a comprehensive perspective in neural network, with the lottery tickets being one of the central themes. It will take place in a few days, and it has a very interdisciplinary collections of speakers and organizers from algorithm, hardware, and even cognitive science. So we have, I think we have good visibility already. We have attracted, as a workshop, we have over 60 submissions and nearly 10 speakers. It will take place in 2 days. So you are still welcome to register the workshop, and the attendance is free, and I look forward to seeing many of you there if you're interested. Now I'm done with my talk. Thank you very much, and thank you again for having me today.
Thank you, Atlas. So very exciting work. And any questions from the audience?
So I have actually one quick question. Thanks for the great talk. I learned a lot from different aspects of it. And you may have already answered this question, so my apologies for that in advance. My question is, you talked about the transferability of these masks across different tasks, obtained from a pre-trained network. The question is how robust these masks are given different initializations of the original dense model.
They are not robust at all. And that is not the point, because the lottery tickets is already, well, in most cases, lottery tickets is defined as a coupling between the initialization weights, even they are random, and the associated mask.
Understood. No, that was actually just out of curiosity. I understand how it works, but
yeah.
Okay, cool. Thank you.
And the same case for pre-trained as well. So the one pre-training, one mask, they are coupled. Yeah. Sorry if I didn't make it clear.
No, thank you. And so you mentioned about the structural, or they are like a structure-based mask. You mentioned something about that sensitivity. How does that relate then?
Oh, that one is just trying to demonstrate the mask is not just a random sparsity that works. It needs the structure that we take effort to make it happen. So we just change some locations of the non-zero elements.
Cool. Thank you very much.
Thank you.
Other questions from the audience? So at last, actually, I have several questions. And so the first that, so have you ever considered that, so since you already investigated that to apply the lottery ticket to the NLP BERT model and also on the CV, so have you done the experiment on the lottery ticket on the current the vision transformer model, something like that?
Yes, one of my students is looking at it now. Although we are, I'm always trying to find a good argument for me to do one new research. You perhaps noticed when I introduced my computer vision, while we're doing the computer vision, I cannot help but spend a lot of time arguing why this is a new research question rather than repeating just the BERT work once again. For vision transformer, I'm having a hard time to convince myself that's yet another interesting work, but one of my students is trying that anyway. We haven't had a result yet, but I didn't see a reason why it shouldn't work.
Thank you. And another question is that, so in the last of your talk, so you mentioned about this to investigate the structured sparsity for the lottery ticket. So here the structured, so you mean that is kind of like similar like the channel pruning.
I'm talking about the channel pruning to find a lottery. Use iterative channel pruning to find the lottery tickets. Yeah, the trick here is channel pruning. Actually, many people have tried channel pruning on lottery tickets before, and it didn't work. The conjecture here, in a non-rigorous sense, is channel pruning each time removes a bulk of information compared to unstructured pruning, which maybe just scratch the surface of every piece of necessary information. So channel pruning, since they remove information in bulks, it's generally harder to recover them, and it moves the network weight further away and harder to recover from the original point. So it's just because, well, it's harder because it's damages the brain harder. But we are recently trying to circumvent this problem by creating some softer form of channel pruning as an intermediate status, and we see some promise that can work.
Okay, so do you consider some other type of the structure, the sparsity, but kind of not channel-wise?
Yeah,
can be many granularities, right?
Yeah, that's true. Actually, for example, we do have a recent work called Early BERT in ACL this year that extend our own early BERT pruning idea to transformers. And there we also, because we claim training efficiency, so we introduced tickets in early training, and there we prune attention head of BERT models. So that's one thing we did. And another thing is, we have recently discussed with expert from compiler design, and I was educated that in compilers, there are different flexible form of sparse filters or the sparse patterns can be utilized. And in principle, they should be as easy to implement in our framework as channel pruning, and we will look at as a future work.
Okay. And I think there's one question from the chat box.
Yeah. So this may be a naive question regarding the benefit of transferability that we can find winner tickets on small data set and apply result on the huge data set. Okay, so transferability has multifold of definition. In my talk today, the major component is on the transferability between different tasks. So find on one pre-training data on pre-training task and transfer on downstream task. So it's a task level. The data level transferability has been looked at by other prior works like this one. The one ticket wins them all. So, they did show that you could find a winning ticket on one data set and make it work on other data set. But experiment basically suggests that it works when the source data set is a big one and the target data set is a smaller one. I perhaps never see a successful experiment that you can find a ticket on CFAR and transfer that on ImageNet. I perhaps never saw that. Forgive me if I'm wrong. I just don't remember. So I don't think that has been experimentally validated yet. But you can find a big one and transfer to other small downstream tasks. And in pre-training, that's generally the case too, right? Pre-trained data set is usually huge. The next question I think is not mine.
Okay. I think the next question, so it's for me. So where the recording of this talk available soon and where? So yeah, so I will upload the video of this talk on the YouTube. And so you can, so how to find that? So for this talk's recording and all the previous recording talks, so you can find that. So Google my name and Rogers, and then you can find my personal website, and then we have a tab there, so including all the information of this seminar, like the time, the time and date for the upcoming talks, and also the previous recorded video link on the YouTube. Yeah. And any other questions from the audience? And if audience don't have any questions, so I will ask another question. So actually, I once asked this question to the Jonathan when he gave us talk. So for the lot ticket, we know that this is it investigates the sparsity of neural networks. So I know that you also once have some publications on the compression using other approaches like the quantizations and the low rank. So do you think that is any possibility to apply the lottery ticket hypothesis, this kind of philosophy to the other compression approaches?
Very good question. Yes, I can tell you confidently that it works for quantization. I can say that because we hope to announce that result very soon.
Okay, that's great. Look forward.
Low rank is a different story. Low rank, I think it basically means if you could, this is actually, I think it actually reduced to a classical signal processing question called sketching. So how you can quickly identify the low dimensions in the data without seeing the full data or even before seeing the full data. I personally tried that a little while before without bearing the name of lottery tickets. It's called Subspace Network and was published in KDD 2018. Basically give some preliminary result of how you could learn a low rank structure online from streaming data without seeing all the data in offline batch mode. So that's perhaps one of the closest thing I know about extending the concept of lottery tickets or low rank. But forgive me, I don't perhaps know more about that, and I didn't continue experimenting lottery tickets low rank.
Okay, yes, sketching like the tensor sketching, that's a kind of very classical approach.
Exactly. I tend to think if a low rank lottery ticket can happen, the technique may very likely be related to matrix and tensor sketching.
Very good insight. Yeah, I think we can discuss more offline about that.
Sure.
So, any questions? Okay, so if no more other questions, so let's thank our speaker again. So this very insightful and very informative talk, and actually I learned a lot from this talk. And also thank everyone to attending our today's seminar talk, and look forward to meet with you, all of you again next week. Thank you.
Thank you for hosting this event, and thank you for your time. Bye-bye.
Thank you. Have a wonderful time. Bye.